All right. So thank you for the invitation and thanks for coming to listen to this talk. So yeah, let's just start with a setup maybe. So T is going to be a topological dynamical system. X is going to be a compact metric space, and T is going to be an invertible continuous map of X. That's the setting for most of the talk. Sometimes I will discuss maybe a smooth case where X is going to be a manifold and T is going to be a map or a flow on the manifold. Maybe then we are going to use some different notation, but for most, at least in the first part, this is notation. And then we are going to, one object that one studies is invariant measures. So these are measures that are invariant by the map. And then we know that the set of invariant measures is non-empty. That's a classical theorem. And one interesting dynamical topological property is unique ergodicity. And this is saying that the set of invariant measures is as small as it can be. So there's just one invariant measure. And from the point of view of the time evolution of our system, this is a very useful property, as for example, this proposition here shows. So it turns out that if I have, it's an if and only if condition. So having only one invariant measure implies, or is equivalent to the fact that for any point X and for any continuous observable, the averages, regular averages, converge to a constant, and the constant has to be the mean, so the integral of f with respect to the only measure that's invariant, which is necessary ergodic. And let me just remind you that there are almost everywhere versions. So like if you take any ergodic measure in the set of invariant measures, then the convergence holds for almost every point. But actually for us, it's going to be important for the talk. I think a good motivating property is that of unique ergodicity. So we want to study every X in the system for say non-classical averages. So here, as you see, we are averaging over the integers up to n. And in the talk, we are going to be interested in more general versions of averaging. So the most general formulation probably one could give here is that of things we are going to be interested in is that we have this topological system, and then we take a bounded sequence, and then we take the weighted averages, right? So this is the thing we consider. Of course, you need to make some assumptions on the sequence. Again, you can't take the sequence to be constantly equal to 0 and so on. But essentially, the thing is already difficult with some simple examples. So for the talk, we are just going to focus on several cases. So let me just tell you that the most classical case, so taking an equal to 1, we go back to the classical averages, and then we know what to do if we want convergence for every point. Some other functions or some other weights that are going to be interesting, we are going to be interested in, people are studying are, say, the Mobius function or the Liouville function. I'm going to recall it on the next slide. And later in the talk, especially for us, case number 3, so a characteristic function of prime numbers is going to be the the case that we are going to mostly consider. And maybe at the end of the talk, I will also comment on the case where we take characteristic function of numbers that are products of at most k primes, where for us k is going to be equal to 2. And this is the last part of the title, so the semi-prime semi-prime theorem. And let me point out that we are interested in every x, and for the whole talk, this is going to be the case. And there is a very deep machinery that's still being developed, initiated by Bourgain in 1987 to prove almost everywhere results. The techniques are, I would say, drastically different if you want to prove an almost everywhere result based on generalizing maximal inequalities, use circle methods. Probably in Mariusz Mirek's talk, you will see some more developments of this type of convergence. All right, and so our goal for the talk is to study mostly point 3 and a little bit of point 4. But there has, in the past 12 years or so, there has been very big development in studying averages where we take the weights to be the Mobius or Liouville functions, or more generally a multiplicative function. So let me just recall the definition. So the Mobius function is well, -1 to the power k if n is square free, and sorry, it's -1 to the power k if n is a product of k different primes, and if n is divisible by a square, then it's 0. And for example, the Liouville function, you take -1 to the number of prime factors. And the important property of both of these functions, and actually you can consider more general multiplicative functions, is that they are multiplicative. Well, I think the development started with Sarnak's conjecture, which gives us a condition conjecturally that's equivalent to, say, plays the role of unique ergodicity in regular averaging, where we average with Mobius. And the condition is very simple. It's very nice. So the restriction here is that the entropy of T should be 0. The topological entropy of T. So HT denotes the topological entropy. And then we see that the conjecture says that you should, the averages, if you divide by n, this should go to 0. So notice this is, as this assumption is very, I'd like to say very mild, right? It should, the way to understand it is that the Mobius function fluctuates so much that you can't capture it in a 0 entropy system. And this is what I just said. So 0 entropy plays the role of unique ergodicity. And now I would like to, so as I said, later on we are going to focus on primes, but I would just like to very briefly summarize some developments around this conjecture, what inputs the development used, which is interesting on its own, but also like we will be able to see later why primes are more difficult than Mobius. So yeah, so as I said, there has been many systems for which Mobius disjointness was proved. So Mobius disjointness, just the statement above. And this was, I would say, the two main driving forces was a breakthrough by Matomaki Radziwiłł in 2015. So they were able to show very strong cancellation of, a very strong result on cancellations of Mobius on intervals of size that goes to infinity. Here I want to emphasize the fact that the h can grow to infinity with x as slow as you want. I think this is what makes the result so powerful. And also, like, there have been further developments. So I think the most recent result is by Matomaki, Radziwiłł, Tao, Travainen, and Ziegler, which I didn't write it, but you put here polynomial phases, and it's not as strong as the original theorem. But just to say that a natural generalization of this goes into studying maybe first exponential sums, where you put e to the n alpha here, right? And this was done by Matomaki, Radziwiłł, and Tao, and then you can put e to the pn alpha, or e to the pn, where pn is a polynomial, or like you can put nil sequence here. So this result, especially the Matematica-Radziwiłł theorem, was used in heavily in many proofs of Mobius disjointness for many systems and generalizations of those. And the other one was from the point of view of dynamics. So I'm talking about, you know, things that allowed prove it for various classes of dynamical systems, was this criterion that, well, first, Debussy, Katai, Bourgain, Sarnak, Ziegler, which says that if you want to show that a sequence, a general sequence, is orthogonal to Mobius, meaning that you have cancellations here, you need to understand type 2 sums, so expressions of that form, where P and Q are sufficiently large different primes. In fact, you can maybe discard a very small set of those, but that was the criterion that initially, I think Bourgain, Sarnak, and Ziegler used it to show Mobius disjointness for the horocycle flow, for example. One important thing is here, and this is the big difference I want to emphasize with when soon we are going to be talking about primes. So the big difference here is that P and Q are fixed in the beginning, and then you let n go to infinity. So this is important from the point of view of dynamics because, right, if you just take xn to be f, t, and x, the sequence that you are interested in, the dynamically defined sequence, then you need to study expressions like this. And this is an object that's at least that it's been introduced in ergodic theory more than 50 years ago, and it's been studied quite a bit. So we are talking here about joinings. So what you take is you take TP cross TQ invariant measures on the, so notice this is nothing else but the regular ergodic average, right, for a different transformation. And then the transformation is just TP cross TQ. And now if you can show that, you know, the ergodic averages of TP cross TQ go to, well, are small O of n, then you get Mobius disjointness. And this was used in many papers on the subject, I think initially in the paper on horocycle flows. Right, but yeah, so the two main tools were arithmetic properties of Mobius on short intervals and type 2 sums, which turned out to be equivalent to studying joinings of TP and TQ, right? And then for many systems, so the idea is, very rough idea is that if your system is sufficiently periodic, say, like it has, you know, it looks like identity along a sequence of time sufficiently rigid, say, then you can invoke this theorem maybe in arithmetic progressions, but for systems of low complexity, and this was also used by Girren, for example, Girren-Wang, for systems of low complexity, this is a powerful tool. It's not as powerful maybe for systems of higher complexity, like horocycle flows, but then quite often you are saved by the fact that you have the other criterion that roughly says that if there are not too many joinings in your system, which maybe quite often you can prove, like unipotent flows, this is work of Peckner or nil flows, so on, then you can also get Mobius orthogonality. Okay, now as I said, we want to study primes. So the object that now we are going to switch to is going to be just this. So we are going to assume our system is uniquely ergodic, even though you don't need it for the further discussion, but it just maybe simplifies several things. And then, well, we talk about the PNT for the system XT. If for every point, so again, I emphasize we take every point, and for every observable, the limit sampled along primes exists. And it's different than Mobius orthogonality, right? The characteristic function of prime is not multiplicative. That's one thing I want to say. And the other thing is that it's natural to assume that the entropy is 0. Just, even for Mobius, it's necessary. And this problem seems to be harder than Mobius. That's the assumption one could make. And then the question is, so what I would like to say is, now for the next few minutes, there are some systems for which this was proven, a prime number theorem, so the limiting behavior along primes was proven. And I would like to focus on, I will state the results. It is also, I think, most of them are also past 10 years. So I think the development around Mobius kind of also produced some development along prime averages. But yeah, I would like, so you'll see why maybe this problem is way more difficult than Mobius. And we will say what we can, later on we will say what kind of, what kind of new tools one could hope for. So, right, so let me just state some classical result. Maybe I won't spend too much time on it, but 1 and 2 are just really, there is not much dynamics there, so it's just the standard PNT. Now, an important result not only in terms of the result itself, but a developed method is Vinogradov's result from 1937, where he proved that an irrational rotation, so here alpha is irrational. If it's rational, then it kind of reduces to rotation on a finite set. So Vinogradov showed that for an irrational alpha, we have this estimate, so a PNT holds. And actually this result is important because it turns out that the method used by Vinogradov is up to very recently essentially the only method that one could use for primes. Like I said, in recent 10 years, and I'm going to discuss that, there have been some new methods. First of all, let me just say that with Mariusz and with Max, we proved that a PNT doesn't need to hold in general. So like if you look at Mobius, right, the conjecturally it's just the entropy. Here we constructed a map of this form, a very simple map of the two torus, the skew product with a continuous G. And this map has all nice or many nice ergodic properties. It's minimal, uniquely ergodic, entropy 0, but it doesn't satisfy a PNT. And some earlier results were given by Ronnie Pavlov, but it's hard to say what the entropy there was. So our example is of 0 entropy. So this is just maybe to say that you can't hope for.
I think that one of examples of Pavlov is for distal systems in higher dimension, and distals always have 0 entropy.
Okay,
so
maybe
he has more than one example, but his example in distal setup would answer this question.
Okay, good.
So distal systems are known to have 0.
Good. So thanks, Vitaly. So probably you're right that distal systems would also.
And your system is also distal.
Yeah, but he does symbolic, I think, distal systems.
But then I demanded connected space, and he did it in higher dimensional distals.
Okay, good, fine. So fair enough. So this is maybe not. This is just to say that you can't hope for a general theorem like entropy 0 or like a simple ergodic or topological assumption that would imply a PNT. I don't think it's known if you can have, if you work in smooth dynamics, for example, you would be interested to know if you can have a smooth example. So here it was very important that the function is continuous, and it's not more than continuous. And I think for Pavlov, it's the same. So there is no C1 map, for example, or C infinity even more, for which it would fail, even though probably the general belief is that it should fail for some maps. that are smooth. Okay, let me talk about recent results. So now, there is no hope for a general result. So what is known? So and as you see, all the results are recent, and I've kind of splitted them into, as you'll see, into 2 or 3 groups, maybe, depending on the method that they use to prove the PNT. So a very nice result in 2008, which also gave a solution of the Gelfand conjecture on, distribution of sum of digits of primes in Q expansion, was the paper by Madhuri-Riva, and this was related to the 2-more sequence and the Rudin-Shapiro sequence, and then generalized for a larger class of what's called automatic sequences by Clemens Milner in 2017. Then we have a paper by Green and, it's 2 different papers. So they produce some symbolic systems of very low complexity that satisfy a PNT. Then there is a result of Green and Tao where they showed that if you take a nilpotent Lie group and the lattice in it, and you take a nil translation by an element, then it satisfies a prime number theorem as well. So I think this is a very large and natural class of systems that are studied. Right, it generalizes, if you think about it, what the nilpotent group is, it generalizes the Vinogradov result for irrational rotations, right, where the group is just abelian. Then Peter Sarnak and Ubis they had a paper on orbits of horocycle flows and for the horocycle flow, and they couldn't show a PNT, as I understand. They couldn't show density, but the result is very interesting. They could show that if you sample your point along primes, then it enters every set of diameter, and maybe 4/5, something like this. Like if the diameter is sufficiently large, then the prime orbits gets enters there. And this maybe could be a good illustration of why, or at least one of the reasons why prime number theorems are more difficult to get than Mobius. So for example, for Mobius, it's known, and this was one of the first paper in the subject by Bourgain, Sarnak, Ziegler. Here it's far from being known. And what's I think worse is that the method that one can use is, the limit is what they've obtained, it seems. And the method in all these papers that I've listed, that's why they are listed on one slide, is the method of type 1 and type 2 sums. So if you remember, type 2 sums, they appeared earlier for Mobius and they were related to joinings, but here they will appear in a rather less pleasant way from the point of view of proving things. So let's see. So criterion for PNT, and this is the method of type 1 and type 2 sums that all these results used. So what you want is, if you look now, the first type 1 sums, what they say is you sample your sequence at an arithmetic progression of size d, and type 2 sum, the important thing is here, maybe it looks a little bit complicated, the average, but right, so here you are sampling your system at, it's a bilinear, so it's a type 2 sum, so d1n and d2n, right? So this part here looks like Mobius. The problem is that the d now depends on n, right? So before you could fix d1, d2, which we called p and q, say. Now this depends on n in a very strong sense, right? That's the first complication. So there are at least 5 complications here. But,
for the record, there's a very nice lecture of Kevin Ford here at the Institute. You can watch it on a video from a few months ago, where he and Maynard explain the sieve limits for type 1, type 2 sums. So in other words, they give you the exponents. So if you think of it just abstractly, they essentially determine the sieve limits, which before it was more an art, now it's a science.
Okay.
So it's worth, if anybody's interested in the limits of what you need abstractly to get what you want, the primes, by levels of distribution, they have really, I think, clarified that.
Okay. Correct. Okay. Thanks. Yeah, so the problem, if you look at these two expressions, let's just talk about type 2 sums. They are usually more difficult, even though type 1 sums are non-trivial as well. But, you know, type 2 sums are the ones that in applications, for example, I think in the paper of Sarnak and Ubis, they could get type 1 to the level that was usually, that one usually needs to. Type 2 was where there were problems. So if you look at this expression here, first of all, you see you need some quantitative bound in terms of n. Maybe the exponent 22 is not optimal, but definitely you need more than 2 powers of log. And I think a bit more than that. Second, complication comes from the fact that D now is allowed to depend on n. And you see, so we are sampling along progressions that depend on n. And in the class, maybe there are improvements to that, but classically you want C0, so the level of distribution for type 1 to be like 1/2 minus epsilon for every epsilon, and C1 you want 1/3 minus epsilon. So these are really definite numbers, and they're, well, one could say they're big if you think about it this way. And then the problem is, you know, you don't have, these are not joinings for at least 2 reasons, right? Quantitative on the right-hand side and D depending on n on the other hand. So you can't hope for, right? You can't hope for just purely ergodic theory tools with no extra input to be able to get primes. And if you look at these papers here, you know, the systems that were studied here, they all have these extra structure that essentially make studying type 2 sums easier, right? Maybe an extreme case, an illustration of that is that, and this is actually Vinogradov, if you study a type 2 sum for a rotation, this is just a type 1 sum because it's a character. So if you take E, right, E to the n alpha, D1 and D2, you can, right? If you have a character, you can, so there are, for rotations, there are type 1 sums only that appear. And also, I mean, it's highly non-trivial, but this may be the very, you know, initial idea how to be able to get the nilpotent groups, right? So there is also a natural class of functions that one could work with. For other systems, like for example, for horocycle flows, we have relatively good thanks to the work of Ratner and Dani, we have good understanding of joinings. And they were able to make it quantitative, the Dani's theorem. But generally, you know, if you talk about general dynamical systems, it's hard. It's just that you need something extra. Yeah, so this is maybe what I just said. The main obstacle is that if you look at this, it's very hard to study in general. There is an F missing, I think, here. So this was the main obstacle. There is one, there is one more method. You know, one could ask if how much Mobius is related to primes, right? Roughly. So if I have Mobius disjointness, how much can what can I say about primes? And so there's a result of tau which says that if you have Mobius disjointness, okay, for any D, but the D is fixed in advance. So these are expressions we like. So this is Mobius disjointness for the map T to power D, right? If you have Mobius disjointness and you have what's called type 1 sums, right? So now notice you don't have type 2 sums anymore. You have type 1 sums only. then you can show that the sequence xn satisfies PNT. So this condition here involves only type 1 sums. The problem with it is that in terms of the previous slide, it would be, you know, up to an infinite level, say. So M here, the M might be much bigger than the N. So then it's like, if you think about it, this expression is like completely different than what the regular type 1 sums tell you, because the step, the M is just much bigger, so you jump by more than the length of the orbit. So this is not something you often, easy to study. One point I want to make is that this can be made quantitative in the sense, and this is some improvement, in the sense that if you have Mobius for D that depends on N, say is polynomially large in N, in capital N, then maybe you can do M up to a level of N to 1/2. Okay, so I don't want maybe to comment much more on that unless there are questions, but right, so if you have no quantitative information on Mobius, you need type 1 up to every level. If you have some quantitative information on Mobius, then you can study type 1, and this is actually something that will appear later. One more method. So far we had the type 1, type 2, which was most successful and most classical. Then the method of tau, which I don't think it was used. So I mean, you know, it's a method, but I don't think it was used. Now, in 2014, Bourgain was able to produce a class of 3 interval exchange transformations. So this abbreviation here is interval exchange transformation that satisfies the prime number theorem. And generalizing the method developed by Bourgain, Ferenczi and Modui were able to show classes of interval exchange transformations on any number of intervals which satisfy PNT. And these were first first examples of weakly mixing systems with PNT. So if you look at maybe I won't go back, or maybe I will. If you look at all these systems here, they are not weakly mixing. The reason is, you know, if you are not weakly mixing, you can hope for a natural class of function. If you're not weakly mixing, you have at least, you know, you have some eigenfunctions, which means that there is a nice class of function to begin with. But if you are weakly mixing, you will see that the method kind of escapes from primes as far as you can and only uses dynamics. And I think this was the main contribution of Bourgain. So the method is very simple when you look at it. It's just hard to to apply or find systems. So if you look at lambda is the von Mangold function. So instead of, you know, sampling along primes, you can consider the sums against von Mangold, and then you have this identity, which is just follows from orthogonality of characters, right? And then the method that Bourgain used was, okay, say we have some good bounds on for nice theta, say in minor arcs, for example. We have good bounds on exponential sums over primes, or the von Mangold equivalently, which give us saving of size log to power an, right? So this typically would be n over any power of log. And then the method is, okay, you take the bound that you have here, you pull it out, and then you have to study this. But if you think about it, the gain that you get for exponential sums is only logarithmic, which means that you need to be able to show systems for which you have this bound. So you consider the ergodic average up to n, right? And you take what's called twisted integrals. So you twist it by the phase theta, and you need to be able to show that it's less than a power of log. And notice that this is difficult. I mean, even if theta equals 1, say, then you are talking about a system whose ergodic averages are bounded by a power of log. And in fact, such systems are hard to get. So I think the hard part in Bourgain's work is producing IETs using very strong periodicity and Katok construction to produce IETs, 3 IETs that have this bound. And just to maybe, if you are not so much into interactions with number theory, like from the point of view of dynamics, a very simple sounding question, and ergodic averages is, I believe, open. So there is no system that would be, say, a smooth system for which the ergodic averages are small o of n to 1/2. So in other words, take a smooth dynamical system. Either it's a Diophantine rotation, and if it's a Diophantine rotation, then every smooth function is bounded. The ergodic averages are bounded. On the other hand, if it's not a Diophantine rotation, then for all known dynamical systems, the ergodic averages without theta even. Theta only makes things worse, but even without theta, the ergodic averages immediately jump up to n to 1/2. So there's like a huge gap. So there are rotations which have 0, and then there is n to 1/2. So if you think about Neal flows, horocycle flows, like unipotent flows, all of them, and actually all known smooth systems have this n to 1/2. And the reason is, well, basically, if you are fast mixing, like, for example, if your system is Bernoulli, then you have n to 1/2. Like if you have a Bernoulli shift, then you have n to 1/2 because you have central limit theorem. And if your system is chaotic enough, then you can imitate the way of proving CLT to show that it goes up to n to 1/2. Yeah. So, okay, so this was just a side remark to say that this is very difficult to get. And actually, yeah, we don't know any smooth system for which this would hold, except rotations, of course. There has been, this expression has been studied, for example, for horocycle flows, I think by, maybe first by Venkatesh and then by Flaminio, Forni, and Tanis, but here what they get is n to 1 minus delta. So it's very far, for some positive, but very small delta. So it's very far to, from being solved. All right, so now I think we are going to go to the results that I wanted to present, which are most, I mean, in a large part based on joint works with Mariusz Lemańczyk and Maxim Radziwiłł. Yeah, so let me state that this is going to be a theorem with slides. The first result is, with Mariusz and Max, is that if you take this system x plus I alpha y plus g, so and g analytic, that's very important. And what we have shown is that if T is uniquely ergodic, then it satisfies a PNT in that sense. One interesting thing to maybe notice here is that a few slides before I told you that if G is only continuous, then these are examples for which a PNT fails. But if you, so here is a, if you increase the smoothness, and actually we need to go all the way to analytic, then you can hope for a PNT. Then theorem 2, I'm presenting them on one slide because in a sense they use similar basic idea, and the idea is to avoid type 1 and type 2 sums for as long as possible. At some point they will hit you, but you want to make it as late as, so what I was, so the two theorems that I worked on was that you can find a weakly mixing time change or reparametrization of a linear flow on the torus for which satisfies a prime number theorem. And theorem 3 was motivated by, partially motivated by the work of Sarnak and Ubis, so they studied the horocycle flow and
Sorry, can I take a question? Can I also take a question?
Yeah.
Weak mixing means all orders?
Yeah, so weak mixing, implies weak mixing of all orders. Yeah.
Thanks.
They are still very rigid, these systems. I'm going to actually spend maybe 5 minutes to discuss this theorem, because this theorem has maybe the system is simple. I will maybe draw it. And and then in theorem 3, what we are interested in is just to, like horocycle flow are mixing. There is no known mixing system which satisfies a PNT. So I was trying to find a mixing system for which a PNT would hold, but I failed. But I could prove density. So, a little bit better than, now, I would like to comment first on theorem 2, even though it's maybe not chronological, but the system is, and the method is maybe best seen here. So what do we do? What is the system? The system is very simple. So you just take the vector field on the two torus generated by 1 alpha, which gives you a linear flow in direction alpha. So a very simple dynamical system. And then you rescale the time. So you multiply the vector field by a smooth, say, analytic positive function g. This way the orbits stay the same, right? And your system, I don't know, maybe I can draw it here. Your system then can be represented as, so there's some g here, and your system is just what's called a special flow over an irrational rotation, where you, and under the roof g, where you identify, so you flow up, right? Once you hit the roof, you go down, and then, or you might view it on the two torus. It's just that you change the speed, right? You don't move with uniform speed. And then we show that this is weakly mixing and it satisfies a PNT. And in fact, for a dense set of functions, you can show that the PNT is quantitative. So one thing I want to point out is a classical theory that I think goes back to Kolmogorov, tells you that if you take a Diophantine number alpha and a sufficiently smooth function, depending on the Diophantine exponent, but definitely analytic or infinity functions, then the flow you obtain by reparametrizing is smoothly conjugated to the linear flow, to the original flow you started with, and hence not weakly mixing, right? The big achievement, maybe initiated by Katok in the 70s, was that you can, if you take a number that's sufficiently Liouvillean, you can produce weak mixing for the reparametrization. And now the good thing is, or the bad, I don't know. Yeah. Well, the thing is that one can only hope for type 2 sums for very small range of these, like not even a power, it's n to 1 over log n, something like this. So, in this theorem, you can't use, So I want to, the theorem here, once you believe certain things, it's easy, like certain big theorems, it's not so hard. So let's maybe go over this. One comment that I want to make, this is where actually I learned about this method of tau, is that if you make this method quantitative, you can use it to get a co-distribution along a subsequence, but not a PNT, just, there is a subsequence along which it holds. Now there is one technical, maybe not that technical. So how do we construct the alpha? Remember the flow we are working with is there are two parameters, the irrational number and the analytic function. So the irrational number is, I think, way more interesting. So what you want is you want two things, or three things. You want Qn to be a prime number and Qn plus 1 to be exponentially large with respect to Qn. So you see here is where the Liouvillean condition comes in. This is mostly for weak mixing. So as I said, if you were Diophantine, you would be conjugated to the linear flow. From the point of view of number theoretical applications, this condition is more important. So what you want is you want to be able to count primes in arithmetic progression up to a level 1/2 plus something small, plus 100, right? So we are saying, how do we construct our alpha? We are going to construct the alpha by constructing the denominators. And that's the way to construct them. And how do we prove that such a set of alphas exists? The main engine here is the Bombieri-Vinogradov theorem, right? So if you look at point 2, which is, I think, the essence, the most important part, is that you have distribution in arithmetic progressions up to level 1/2 plus something for Qn. So Bombieri-Vinogradov tells you that most numbers are like that, and you pick those. And it's not that simple because you need to simultaneously worry about condition H1, but roughly it's not a very difficult one. And the other thing is you use, so the dynamics is captured on this slide. So what you want to know is that your map is very rigid, in a sense that if you take along powers of the denominators, the map, as you see, is like an identity for many Qs. And then I will present just one proof for the case or sketch. It's not very difficult, right? So what we do is we take p less or equal than n, and you'll see why we need this assumption. And then you split it into residue classes mod n, right? Then you know that your p orbit along p, right? If p is equivalent, is congruent to a mod qn, you use this, right? So p is here, and you can say that dp is just the residue. And then you use the fact that psi is smooth. So instead of kp, you say, okay, I have ka, right? This turns into ka. And then instead of, summing over kp, you count the number of primes that are up to n, and they are a mod qn. And essentially up to some details, you use, well, the fact that alpha was chosen, or the denominators, to satisfy the Bombieri-Vinogradov theorem. And this then is, this is an error that's not important. And this here is uniform. We don't care so much what it is. It's just that the Bombieri-Vinogradov theorem tells you that it doesn't depend on A. So, and the fact that Qn is prime actually makes it all work here. Otherwise, I would have to take the Euler function and skip some residue classes. But because Qn is prime, this helps a lot. You can pull this out, and then you have the regular ergodic average. If you see this, and our map was uniquely ergodic, so you can say, okay, I have some cancellations here. And if you want to optimize, you need to optimize this average here, and you optimize it by taking psi to be a coboundary, then you get a telescopic sum, and this sum here, just the ergodic sum, is bounded by by big O of 1. For the general case, where you can't approximate because your n is too large, you can use the result on the primes in short intervals, but now the moduli is much less. So what happens in the other case, and this I'm not going to have time to comment much on that. In the other case, you just split into intervals of size 1/6 plus epsilon, and you essentially, it's like Ziegel-Waalfisch in short intervals. So if you're in case 1, you have one long interval. In case 2, you have short intervals, and then you use this theorem kind of on each of the intervals you have. You split the average up to n into intervals of that size. And the way you chose the parameters, so 1/6, 110, 100, makes it all kind of cover all the possible cases. So that's maybe the idea. Of course, so the idea here is, as you see, we didn't use type 1 or type 2 sums, but of course they are hidden in all these results here, right? So if you talk about Bombieri-Vinogradov or this one, it is there. So now one more thing, maybe before I finish, is I wanted to say what happens for this map. So this is a theorem with Mariusz and Max. If you have a skew product like this, so the key dynamical proposition for the weakly mixing case was this periodic approximation. But if you think what happens for this map, I'm not going to be able to give more details, but it turns out that it's not any more rigid in the sense that it returns to itself, but you get a polynomial phase here. So Pnx is a polynomial of, say, large degree, and we have some control on the coefficient. So the dynamical input is much more difficult. I mean, it is what it is. It's way complicated because you have a polynomial. In the previous one, the polynomial would be 0. And then what you need to use to kind of apply the strategy from theorem 2 is, and this is what we do with Max and Mariusz, is we improve on the result of Matomaki and Shao just a little bit. And here is where we need type 3 sums as well. Type 2, 1, 2, and 3. They had the result for 2/3 plus epsilon. What we have is 2/3 minus eta. Eta, we needed a positive eta, again, to cover all possible cases, right? To merge it with the 1/6 here. It turned out that we needed to either go below 1/6 or 2/3. Both of them involve type 3 sums, so we decided to go with this one. And here, what this says is that polynomial phases are, right, you have control on them. Maybe one last slide. So this is the last slide. I said I will talk about semi-primes or semi-primes, so products of 2 primes. And here the new input that we had, again, with Max and Mariusz was, actually, we had it, this criterion here, we had maybe, it's not very difficult. Like 4 years ago, the problem was that we still couldn't find anything where to apply it to. So now what you have, this criterion requires, so if you have type 2 sums up to level n epsilon, notice epsilon can be, a small number, and you have some gain on type 2, then you are equidistributed along product of primes. So P1, P2, 2 primes. And okay, we had this criterion for some time, but as I said, it was rather difficult. I mean, you could construct systems which have this type 2 sum control, but with a recent breakthrough of Elon, Amir Mohammadi, and Jiren Wang, this should give a semi-prime number theorem for horocycle flows, and this is what we are working on. I just want to say that the proof is significantly simpler in the case, in the co-compact case. I would say, like, it's a different level of difficulty, definitely. In the non-co-compact case, one needs to go deeper into results from number theory, and in particular, a nice thing is that you consider 2 cases where there is a Siegel 0 and there is no Siegel 0, because you have periodic orbits. So the problematic case is if your orbit is not close enough to a periodic orbit, but not yet equidistributed, and for the type 2 sums. Yeah, I think that's all. So thanks for.
Yeah.
You say that why analyticity is so useful for you in your main theorem?
The one yeah. So analyticity. So okay, very short answer is that you need to have good control on the coefficients of Pn. I didn't say what they are, but analyticity tells you that they are of the form h to minus I plus 1. So it's like exactly the regime of Matomaki and Shao. If the function is less than analytic, and actually even C infinity we couldn't do, the coefficients start to fluctuate a lot.
Oh, okay.
And then you need shorter intervals, but shorter intervals you would have to go below 2/3 significantly, and you can't do that. Yeah. So the approximation is better when the function is analytic, shortly speaking.
Yeah, thanks for a wonderful talk, really wonderful, and also viewpoint. I have 2 questions. One is, you made clear that the prime number theorem doesn't have a very natural dynamical formulation just in terms of ergodic properties. I think you've made that clear, and that maybe was clear to everybody before, but I think it's much more clear now. But there's another thing that's the elephant in the room here that I think is demanded by your lecture and by people thinking along these lines, is you've got down to semi-primes, and there's something called the parity principle, something observed by Selberg, also understood very well by Ivanich first, which is kind of a limit of sieve methods in order to produce primes, cannot distinguish between the parity of the number of primes, odd or even. And I have a strong feeling that the way this picture is emerging is that the parity principle should be built into the dynamics. And it would be much more profound to understand what the parity principle in dynamics, in this kind of interpretation is. Anyway, I'm just suggesting it's a problem.
Maybe that's a good view. Yeah. I mean, especially with this type of methods, what we want to do is we want to understand what push kind of the input from number theory to the very last moment, like to have results that we know well are classical or believed, say not classical, but maybe believed. So I think maybe you can put that's a good thing, that parity problem at this level and avoid it at this level. Maybe. I didn't think about it, but that's a good comment, I think.
I have a feeling that when you understand it, it'll fit very well into the picture and it'll be quite profound. It's my guess. Yeah. I'm just suggesting it as a problem. Yeah.
Thank you. I'll try to think. Yeah. Thank you.
So I just wanted to point out that exponent 2 times minus eta has been improved to power 8 plus epsilon by mathematician Tal and myself.
Correct.
Your work.
Correct. I probably should have said that. Yeah, you're right. And actually, this was probably like maybe I spoke with Terry in October 1 year ago or so, like 1.5. Yeah. So now 2/3 is if you did it earlier, we could just call you. Probably.
Yeah, that came after yours.
Yeah.
No more questions? And let's thank Adam.